Hi students, I wanted to continue the idea of optimization problems because this chapter more than any I think have really varied problems. They're very different, each of them. So I wanted to go over a few of these that will help you to do your homework, to understand the idea better. So here's another example. This is example 1 of optimization used when optimizing some sort of either a object or a function that's maybe, as you'll see later on, that's going to be either revenue or a cost function. So for this one, it's like we have an open box, has a square base and a volume of 108 cubic inches. Let me see if I can try to draw this. I don't draw too well, but I will try. So it's a square base. Okay, so there's our box. It could be a really tall box. I could make it taller. Maybe I should try that. Well, I'll just leave it. Here's our base right here. Let me just color in the base. There we go. A square base and a volume of 108 cubic inches. We want to find the dimensions of the box that will minimize the amount of tin used to make the box. So any three-dimensional object will have 3 dimensions. It will have a length, and we'll call that x, and a width, I'll name them in a second, and a height. So what's important here is that our box has a square base, which means that the length and the width of the box will be the same measurements. So I can also call the width x. It's going to have a square base, so both the length and the width are the same. Okay? And then the height, let's call it y. It'll be different. You know, this is a really practical problem because companies that make goods, especially that make things you buy like at a supermarket, think about it. They want to minimize the packaging. Excuse me. They want to minimize the amount of cardboard or aluminum or tin. Tin's used, I think it's in like cans, because those things cost a lot of money. So the least they can use, the better, but maintain the same volume in a can or in a box. So let's go ahead. I'm going to take a drink of water. If you could cut this out, please. Here I am. There we go. Okay. So let's think about what we want to find here. We want to minimize the amount of tin used, which would be the area of the tin. But we're given the volume. So we're going to actually use both of these ideas to help us come up with a solution. Let's start with the volume. It's going to be the length times the width times the height. I'm going to use these variables and then we'll replace them with things we know. So we are told that the volume is 108 cubic inches. So we'll replace the V with 108. And then I'm calling my length x, my width x, and my height y. So x times y. Or we will have that we have 108 equals x squared y. We'll use this in a minute. Excuse me. Let's come back and think about what we're trying to minimize or maximize. When you see words like minimize or maximize, it has to do with optimization. It always has to do with taking the derivative. So we want a function, the area specifically, that we can take the derivative of. So the area of this function is what we want to find. Okay. And how would we do that? Well, we can calculate the area of a rectangular surface pretty easily. Let's write a few notes here. So we know we're going to have the base, which is square. So every side of this base is x. And to find the area of a square or a rectangle, you just multiply the length times the width. X times x, or x squared, will be for the base. All right. But we do have a container here. So we have how many sides? 4 sides. So we're going to have 4 times some quantity. So let's talk about the sides. So we had said that our length is x, our width is x, but our height is y. So you can think of the side as like this. A side would look like that, would have x on the bottom and x at the top, and then y and y. So what would be the area of this? It would be just x times y. And we have 4 of them. So we have an equation here for the area that we can use to help us find this, to minimize the amount of tin. The only problem is here, we have 2 variables. We have x and y. We don't want to use like implicit differentiation. It's not going to help us here. What would be better, and what we're going to be able to do, is remember this function here, 108 equals x squared y? Well, we can take that and solve it for y by just dividing both sides by x squared. So we have 108 divided by x squared is equal to y. What are we going to do with this quantity? Plug it in for y here in our function. Let me start here at the top. So we have a of x is equal to x squared plus 4 times x times y, but y is the same thing as 108 divided by x squared. So we can do a few things. We can remove an x from the numerator and denominator, and we can rewrite this as x squared. 4 times 108 will be 432 divided by x. Or since what's the next step we're going to do? We're going to differentiate this, right? So maybe we want to write it in a little more convenient form before we take the derivative, writing it as x squared plus 432. And then remember, if x is in the denominator, if we brought it up to the numerator using our negative exponent rule, it will have an exponent of -1. Now we can take the derivative. Derivative of the area is going to help us find the dimensions of the box, basically to minimize the amount of the tin used. All right, so then we'll have 2x minus 432x, and then what happens here to the -2, because we always subtract 1 using our power rule for derivatives. So what do we want to do to minimize? We want to set the derivative equal to 0. So 0 equals 2x minus 432x squared. Let's go ahead and move the 432x squared to the left side by adding it to both sides. And then that will be equal to 2x. I can divide out the 2. I see a problem here. So let's go ahead and rewrite this with my x squared in the denominator, because that's what should be here first. There we go. 432x to the -2. We're adding 432x to the -2 to both sides. That x to the -2 is actually living in the denominator as x squared. We can divide out the 2 from both sides, leaving 216 divided by x squared is equal to x. And then how do we solve this equation? We multiply both sides by x squared. So we'll end up with, see if I have enough room here. Let me go ahead and erase on the left side here so that I can continue and finish this problem. Okay. So let me make an arrow coming back over here. So let me work with my orange marker again. So 216 is equal to x times x squared, or x cubed. And then we take the cube root of both sides. The cube root of x cubed is just x. The cubed root of 216, what number do we multiply by itself 3 times to get to 16? The answer is 6. So the length is 6 inches. The width is 6 inches. We just need to find the height. So what could we do? We could plug it back in here to find y. We could also replace 6 in the original equation we had for the volume. (108) is equal to x squared, so 6 squared times y. And when you solve that for y, you're going to get y is equal to 108 divided by 36, which is 3. So let me box my answers here and write my answer up here. So the dimensions of this box, we would have a box that is 6 by 6 base and a height of 3 inches to give us a volume of 108 inches. That will also minimize the amount of tin we need to use. Bye, students. See you later.